Hey guys, welcome back to video 4. Today we're going to quickly go over the mathematics behind the tangency portfolio and then work to code it into R. After that, we'll add this portfolio as well as 3 other portfolios to the plot we've been working on so far, and then we'll export a table of summary statistics. The optimization program we're looking at here is an optimizer that finds a portfolio on the capital allocation line rather than the tangency portfolio. We can do this because we know the tangency portfolio lies on the capital allocation line. We're still minimizing the variance of the portfolio, but it's now constrained so that the return of the portfolio achieves the weighted average of the return of the risky assets from the 47 industries and the return on the risk-free rate. We now form the Lagrangian function as we did with the previous portfolios and take the first order conditions with respect to W as well as lambda. So taking the derivative with respect to W yields this first order condition, and again W can be solved out for, and lambda remains our only unknown because we know our covariance matrix C, we know our mean vector of returns, and we know the risk-free rate as well. The second first order condition with respect to lambda yields this expression here, number 2. You just have to be conscious of the chain rule and then distributing the terms when taking the derivative. In order to solve for step 3, we need to realize lambda is just a scalar quantity that creates a point of tangency in the optimizer, and it contains no information on the relative weights of the risky assets. Therefore, we can multiply each side by the excess return vector, and then solving out for lambda and inserting terms from the second first order condition yields the expression in the second bracket here. Actually, lambda has an intuitive interpretation here in that it's telling us how much one invests in risky stocks versus T-bills. However, we know that the tangency portfolio is the only portfolio on the capital allocation line that's 100% in risky assets, so therefore lambda in this circumstance is irrelevant. Therefore, the optimal tangency weights can be represented with this formula. The numerator is a vector of relative risky assets, and you can see that that was derived from our first order conditions, in which in this case lambda is just equal to 1. And the denominator is just the sum of the relative risky weights that ensure the portfolio's weights sum to 1. Okay, we're back in R and are just coding the optimal weight formula we derived from the optimization program. To start, we're going to assign a variable WT for tangency weights, and we're going to multiply the inverse of the covariance matrix by the mean vector of returns from the 47 industries. And you'll notice this is just the numerator from the first order condition that we calculated from the PowerPoint. And then from there, we're going to take this value and we're going to reassign it to say that WT divided by the sum of WT, which is our denominator, should give us the correct vector of tangency weights. I went ahead and calculated the mean return of the tangency portfolio as well as the standard deviation because the calculation is exactly the same as we did with the previous portfolios. So now we're going to move to export a table of the means, the standard deviations, and the Sharpe ratios of the 6 portfolios we've created. The first thing we need to do is assign a variable to create a vector of means for the 6 portfolios. So we'll call that ZMU, and we're going to combine this vector through the C function, and then we'll go ahead and copy the average returns for the 6 portfolios. Next, we'll do the same thing with the standard deviations of the portfolios and assign it the variable zsig. And again, use the C function and combine all the 6 standard deviations from the portfolio. Now, in order to calculate the Sharpe ratio, we're going to assign a variable just z sharp, and we're simply just going to take the excess returns from the z mu vector and divide it by the standard deviation of the respective portfolios. To export a table, we're going to use the right CSV function, and we're going to also use the round function, which will round our final answers down to 2 decimal points. And we're going to use the cbind function to combine the vectors that we've just calculated, z mu, z sig, and z sharp. No capital. And then we're going to round to 2 decimal points, and then we're going to call the file table1. And we'll execute that line of code. To export a table, we're going to use the right CSV function, so right.csv, and we're also going to use the round function, which will round our final answer to 2 decimal points. And then we're going to use the cbind function to combine the vectors we just created. And we're going to combine z mu, z sig, and z sharp. And we're going to round to 2 decimal points. And we're going to finally call this table1.csv. And we'll execute that line of code. And we go to the working directory, or our current working directory. We should have the file saved right here. So if we open this up, and it's a bit slow right now. You can see a table of the mean returns, the standard deviations, and the Sharpe ratios of the 6 portfolios we calculated have been exported to Excel. The last thing we need to do in this video is to plot the other 3 portfolios and add a line of tangency. But first I want to clean up the efficient frontier by defining the plot type. And we'll say plot type equals L for line, and I think that will clean up the actual frontier line a bit. So now we want to go in and copy or paste the rest of the portfolios into the points and the text section of the plot. And we need to do the same thing for the standard deviation. And also remember to update your labels and the position of each of these points on the plot. So we can go ahead and execute this line of code. And you can see that the other portfolios have been added, and that the tangency portfolio you actually can't even see at this time, and the efficient frontier looks a bit cleaner. And finally, to add the line of tangency, we're going to use the segments function, which just draws a line between 2 points. And for the first xy coordinates, we're going to use 0, 0. And then we're going to draw this line up to the standard deviation of the tangency portfolio, as well as the mean return. And if we execute this line of code, you can see that the tangency line has been added, but you can't even see the tangency portfolio because it's so irrational. This is the end of this video, but I hope to see you in the next one. We'll start to look at the out-of-sample performance of the 6 portfolios we've calculated.